I'm very pleased to introduce to you our speaker today, Professor Michael Ruzhansky from Ghent University and Queen Mary University of London, and he will speak about non-harmonic pseudo-differential analysis. So please, Michael.
Yes, thank you. So, yes, it is my pleasure, and I would like to thank the organizers for this opportunity to speak. I see this is a talk which I made a couple of months ago. So, and I gave it already a couple of times. So I see that maybe some people in the audience may have heard this already, but there are some changes, small changes. But anyway, it's sometimes good to hear the same thing twice, maybe. So so I will try to explain. So non-harmonic pseudo-differential analysis. So it is about the theory of pseudo-differential operators based on non-harmonic analysis, and I will try to explain what I mean by this. So I start by some literature, a bit review of harmonic analysis and harmonic, so-called harmonic theory of pseudo-differential operators, or harmonic quantization theory. It is so I understand by harmonic is when we have some kind of a structure, group structure, in particular on the underlying space. So, and here I can mention I was working on, I was developing global theory of pseudo-differential operators on compact Lie groups. So recently also we have an extension of this theory to compact homogeneous manifolds when you have a quotient of one group by another, which covers spaces like spheres. This is still harmonic analysis, and also for operators now we have a version in development of a theory which is of operators acting on vector bundles. But this is all harmonic theories in this point of view. So in a sense, because of the group structure. So this is a compact situation. Then I worked on nilpotent Lie groups, where we have nilpotent group like Rn or the Heisenberg group, where we can also develop global theory of pseudo-differential operators, but again, it's based on the group structure. So we have some also a few works on general locally compact groups, but again, I consider this as harmonic type analysis, lattice, and but here, so and then this is maybe more. And the last one I want to mention: locally compact groups and quantum groups. Again, there is a quantum group. There is some structure on it, and so some versions of the pseudo-differential theory I have worked on this in these directions, but now these are all harmonic. So here I want to present a non-harmonic variant of the theory, and I want to explain what it is. But first, let me remind you a little bit. This is well known. Pseudo-differential operators. So we have like the classical theory of operators on Rn. We have Fourier transform f hat of xi. Xi is in Rn, the dual variable, and then operators. Many operators, essentially one may say almost all operators acting on functions can be written in this way, in a pseudo-differential form, and then with some symbol. And then, of course, one can study some classes of operators if we specify a class of symbols, like this kind of polynomial behavior. Then we have the classical Hermandes theory, Kohn-Nirenberg and Hermandes theory of pseudo-differential operators. Then we can talk about, so I started with this pseudo-differential operators on the torus when we have Fourier coefficients. So now xi belongs to the lattice, but we can define Fourier coefficients, and then we can quantize, consider quantization in this form. So we can also consider operators written as a series with a symbol, and then we want to put some conditions on the symbols, and it's natural to put difference conditions. So x is a variable on the torus, but xi is a dual variable. in the integer lattice, we cannot differentiate with respect to psi, as in the first case, but we can consider differences. And so this goes back to Agranovich, but then some papers also. Rabinovich, Vladimir Rabinovich wrote several papers on this topic. Later, although he used slightly different representations of operators, not in this form, but anyway. So there is some theory on this, but then we extend this. We can extend this to compact groups, and in the case of compact groups, just I emphasize a few differences. So we consider Fourier coefficient. Xi is a representation of a group, so we know that groups are well characterized by their representations. So if Xi is a representation of a group, then we can consider Fourier coefficient. It is becomes matrix valued in the case of compact groups, and then we can consider similar formula. So with a matrix valued symbol, because Fourier coefficient is matrix valued, representations matrix valued, so we can consider trace, but we can consider a symbol. And then we can also define symbol class and then try to develop the theory, which we have developed with Turunen now more than 10 years ago, global theory of these operators on compact groups. So this is the situation. Then, so here I want to, this is a book which I mentioned on the right, the book with Turunen. And then, so the left one is a book with Veronique Fischer, my postdoc at the time. It is open access, can be downloaded for free. And this develops, so the one on the right develops this pseudo-differential theory on compactly groups. The one on the left develops the corresponding theory on nilpotently groups. And then I can mention, just use this chance to mention other two books. The one on the left is with another postdoc at the time, the Ruzhansky, Hardy inequalities in homogeneous groups. So we can, well, it's not about pseudo-differential operators, but about Hardy inequalities and other types of inequalities. It was 100 years of Hardy inequalities. And then another one, spectral geometry of partial differential operators. But these are not related to this talk, but just as so both books are open access. So that's why I show them here, that they can be downloaded for free. And anyway, this is with some colleagues from Kazakhstan, also Mahmoud Sadebekov. Okay, so now I go back. I now go back to non-harmonic analysis. So as I said, harmonic analysis is analysis. There is no. I guess there is no definition of harmonic analysis. Maybe one can check Wikipedia and see what is the definition of harmonic analysis. But for me, and maybe different people have different definitions for themselves. But for me, it is when we have symmetries in the underlying space. And in the case of a torus, classical Fourier analysis is when we consider exponential functions like this on the torus. And Xi is in the integer lattice. So we decompose everything with respect to functions like this. When Xi is in the lattice, then we talk about harmonic analysis and classical Fourier analysis. And more generally, we can do this, as I said, we can work with representations of groups, but this exponential is like representation, character of a group. So then it's a special case of working with representations. So if you work with representations, then in one form or another, then we can still talk about harmonic analysis. However, non-harmonic analysis here, the term comes from the Pelly and Wiener book when Fourier transforms in the complex domain from almost 100 years ago, and they worked with exponential. They were still on the torus Tn, and they worked with exponential functions like this, but they considered Xi to be not in the integer lattice. So somehow they work still with the same functions, but well, with different functions, because non-periodic functions. Xi is not in the lattice, and then they talk about non-harmonic analysis. And there are some in the I think it's not very this term There were some papers by Sidletsky called Non-Harmonic Analysis, but maybe the literature is not so much as for the harmonic analysis, of course. But so here, for me, more generally, non-harmonic analysis, I mean, when we work with, still we work with something, but not representations, but with eigenfunctions. Eigenfunctions, expansions of some boundary value problems on some manifolds, compact, maybe compact, non-compact, with or without boundary. And this kind of analysis was initiated in this paper, non-harmonic analysis of boundary value problems, with another of my postdocs at the time, Niyaz Tokmagambetov, in this paper, which is about 70 pages, and then was further extended by in a few other papers, but recently, so this was about 5 years ago, but this year there was some progress last year and this year. That's why I'm presenting it. I'm presenting this here because it's research continues, and so here. Yes, so I will give some overview of these results, but let me start here with the setting. So the setting is the following: that let's consider manifold M, which can be with boundary or without boundary. So boundary may be empty if you want, but it can be with boundary. I don't assume that it's bounded manifold. And we consider an operator L, some operator with some boundary conditions. So if there is boundary, we can talk about boundary conditions. If we don't have boundary, we can still talk about the domain of this operator, even without boundary conditions. So we fix some manifold, some domain, some manifold, and some operator. And this is our setting, and the assumption will be basically only one assumption at this moment, is that the operator L, which we fix, has a discrete spectrum, and the eigenfunctions of this operator form a Riesz basis. So this is the only assumption, that we assume that the spectrum of L is discrete. Then we denote, so Xi is some discrete, I is some discrete set, Xi is an index, area Uxi is lambda Xi Uxi, so lambda Xi are eigenvalues, Uxi are eigenfunctions. And the condition is that, because we don't assume L to be self-adjoint or symmetric, Uxi doesn't have to be orthonormal, but we assume that it's a Riesz basis, which means that any element of L2 can be uniquely represented in this basis. But the basis doesn't have to be orthonormal. And I want to note, so there is no assumption on the boundary to be regular, and no assumption on L to be self-adjoint. And so already when we consider this general setting, we can say a couple of things, namely Bari, going back to the work of Bari, she considered this kind of decompositions, and then we can consider, so a joint problem will also have discrete spectrum. It will have the same eigenfunctions, eigenvalues with complex conjugates, and it will have also Vxi, which will be a basis. So then she proved that Uxi is a basis, Riesz basis, even don't leave Vxi is a basis. So if we assume that Uxi is a basis, then for the joint operator, eigenfunctions will also form a Riesz basis. And moreover, these families are biorthogonal. As I said, each family is not orthonormal, but they are orthogonal to each other. Delta is a Kronecker, delta Xi eta. So Uxi is orthogonal to V eta. So the situation, and so how do I, why it's not? Yeah. And so the general philosophy, let me, before I show you formulas and calculations, let me explain the general philosophy. So philosophy is the following, that suppose we are given, so we can say like this, that let's take a view backward from the classical Fourier analysis. And we can say the following, that what is a classical Fourier analysis? Analysis on the circle. Of course, this is something that a lot of people work for for a very long time, so maybe well understood. But from our point of view, the classical Fourier analysis is analysis of decompositions with respect to eigenfunctions of this operator with periodic boundary conditions. So we can say that decompositions with respect to eigenfunctions of the operator L on the interval 0, 1 with periodic boundary conditions. Because so this classical Fourier analysis is a special case of the setting which I presented before on the previous slide. We have an operator L. In this case, L is nice and self-adjoint, and with periodic boundary conditions, and it has exponential functions here, eigenfunctions of this operator, and Fourier analysis is decompositions with respect to eigenfunctions of this operator L. So here at the bottom I say Fourier analysis is decompositions in these eigenfunctions. We can say that pseudo-differential theory is a theory of transformations of these decompositions. If we consider periodic partial differential equations, we can analyze them by using such pseudo-differential theory. And periodic boundary conditions, when we develop the theory of operators on groups, on the circle, on the torus, the periodic boundary conditions are embedded into this theory. And so now the general philosophy is the following, that suppose we are given some differential equation with some complicated boundary conditions. And so what we can do, there are two ways. One way is to use the classical theory of pseudo-differential operators, and then people have been using Boutette-Manuel theory, and there are some transmission conditions on the boundary. There are some versions of pseudo-differential operators, Fourier integral operators on manifolds, and so on. So this is kind of using the classical. We can say, okay, we have different boundary conditions, we have different geometry, but we insist on using the classical Fourier analysis. And this is the kind of a common approach to these problems. But here I suggest a different approach. And the different approach is the following, that suppose we have some manifold with some complicated boundary conditions. So what I say is that let us develop a pseudo-differential theory which is not based on the classical Fourier analysis, but which is based on these particular settings that we have. So if you have some different periodic, if you have boundary conditions which are different from the usual ones, then why should we use the classical Fourier analysis? Maybe we should develop a version of the Fourier analysis which is adapted well to these boundary conditions. Or if you have a manifold with some geometry, maybe we should develop a version of Fourier analysis which is well suited for this particular geometry. And then, as I say here, we can develop Fourier analysis based on decompositions in eigenfunctions of some operator with these different boundary conditions. And then we can think of pseudo-differential theory again as transformations of these decompositions, and partial differential equations with these boundary conditions we can analyze using this new pseudo-differential theory. So this is a philosophy behind this approach, and I will show. So let me give you an example. So here I repeat that the classical Fourier analysis, we view classical Fourier analysis as decompositions with respect to eigenfunctions of this operator L here on the interval 0, 1 with periodic boundary conditions. But now let us change this slightly, and let us consider the same interval 0, 1, let us consider the same operator L, but let us consider different boundary conditions. So H, you see there is H here, and if H is equal to 1, then we are in the setting of classical Fourier analysis, but if H is different from 1, then we can, this operator is not self-adjoint, but it is still in our setting, because eigenvalues lambda psi are given like this, and the system U psi is a biorthogonal system. It's a Riesz basis, so U psi is a Riesz basis, and the adjoint operator has, as I said before, it has also discrete spectrum, and V psi are eigenfunctions of the adjoint operator. And so what we can say, So we can do two things. Suppose we have this M, the same many. Suppose we have this boundary conditions. So suppose we don't have periodic boundary conditions, but we have boundary conditions H, y of 0 equal to y of 1. And so there are two ways, right? There are two ways. So we can say, okay, we insist to use classical Fourier analysis for this problem. So suppose we are given some suppose we are given some differential equation or some question of Fourier analysis or something. Suppose we are given some differential equation with these boundary conditions with H, and then we can do two things. As I said, we can say no, we know classical Fourier analysis so well, so we will insist on using classical Fourier analysis even if we have H in the boundary conditions. Still, we use classical Fourier analysis. This is one approach which people have been following so far, I think, and the approach which I'm suggesting here is that let us forget about classical Fourier analysis now, and let us develop Fourier analysis which takes this H into consideration, which will mean that we consider Fourier analysis based on this U size, which have this formula, and based on V size, which we have this formula. And then let us try to develop the Fourier analysis based on these functions, and maybe even more. So before I show you how we develop this analysis, I can say there are other examples. So boundary conditions may be non-local, like here. So there could be some. So there are operator L maybe. So this is example with H in one dimension, but there are many examples of operators in higher dimensions. Operators we can also talk about, like harmonic oscillator, unharmonic oscillator, Landau, Hamiltonian. All these operators, Hermann sum of squares, they all somehow fall into our setting, because what we require, remember that the only conditions we require is that the operator, some operator has a discrete, we choose a model operator, and then we develop Fourier analysis and everything based on Eigen functions of this operator. So if you say, let's say harmonic oscillators, and we have Hermite functions, and then we are still in this setting because Hermite functions give us a discrete Iris basis. Well, in this case, it's even orthonormal basis. And then we can develop Fourier analysis instead of exponential functions, we take Hermite function. And in all these examples, we can do this. Sometimes we know these functions explicitly, Eigen functions. Sometimes we don't know. So these are different examples, and let's see. Yeah, so the Fourier analysis. So let me see how we develop the Fourier analysis. And there are many open questions, I would say, because once we have full Fourier analysis, then many questions of classical Fourier analysis can be formulated for this Fourier analysis as well. And so remember that, so we have the discrete spectrum. So this is the setting. I am recalling we have operator L. We fix operator L. Sorry? Some questions?
Sorry, no. Apparently no. Please.
Okay, so, but please ask me questions if you want. You can interrupt me at any time. So we have a discrete spectrum. So remember, we have a fixed operator L. U psi is a basis, Ris basis, discrete spectrum, and L star will have V psi automatically also as a basis. So let's start to develop Fourier analysis. First, we need distributions. So we need to define what is Fourier transform and what are distributions. And this goes as follows. So we can define test functions, C infinity L, test functions as intersections of domains of operator L to all powers. And because L is not self-adjoint, we have two versions of Fourier analysis. And there will be some interesting interplay between them. So we have C infinity L is intersections of domains of powers of L. C infinity L star intersections of domains of L star. And then we can define distributions as usual as dual spaces for these spaces of test functions, but we define distributions associated to L as dual space to C infinity L star. And distributions for L star as a dual space for C infinity L. So there is this interplay. So here we define Fourier transform of L. So Fourier coefficient of F with respect to L. So L Fourier transform of F as integral with respect to V psi. So V psi, remember, these are Eigen functions of the dual problem L star. And Fourier transform with respect to L star is an integral with respect to U psi, which is Eigen functions of the operator L. So then we can talk about Schwartz. So now we want to talk about. So this is Fourier transform defined for nice functions. Now we want to define it for distributions, and we do it in the standard way. We can define, like, suppose L is a differential operator for the M. Then we can consider lambda psi is Eigen functions. We can consider order 1 over M. So basically, this psi in the Japanese brackets, angular brackets, is like spectrum of this operator L, but rescaled to give us operator of the first order. So we can consider the Schwartz space of the coefficients. These are functions H, coefficients H, which decay as any power of compared to the eigenvalues of the operator L. Then we have Fourier transform mapping C infinity L to this Schwartz space. These are bijective homeomorphism, and we have Fourier inversion formula. And what is interesting here, again, I said interplay, because you see f hat of psi is defined as integral with V psi, but Fourier inversion formula, it is the sum with U psi. So if the operator is self-adjoint, let me say once again, then lambda psi is real and U psi is equal to V psi. So then there is no difference. But here, if the operator L is not self-adjoint, which we insist, we don't want to have self-adjoint operator, because remember, when I modified a little bit Fourier analysis with here, I modified a little bit, I put H, then operator L is no longer self-adjoint with this boundary condition. So, and I want to treat this kind of problem. So I don't want L to be self-adjoint. And U psi, you see, U psi is different from V psi in this case. So, yeah, so if f hat of psi is given integral of f with V psi, then we can recover f as a sum of f hat U psi. And then the standard way, we just by this formula, by duality, we can extend Fourier transform to distributions. So we have now, so this slide gives us spaces of distributions. It also gives us Fourier transform extended to distributions. So we are in a good situation. We can consider, interestingly, we can consider convolutions associated to L and L star. So this is a definition. We can define convolution of two functions by this formula. And if we take these definitions, then this is a nice convolution, which is commutative, which is associative, and the Fourier transform of the convolution is equal to the product of Fourier transforms. So it has nice properties, like if we convolve test function with distribution, we get test function. And we have some, if M is of bounded volume of a manifold, then we have some inequalities like this. But if it can be everything that I said so far makes sense if M is unbounded. And this convolution can be calculated. So for this example, L, when we have H in boundary conditions, and this is convolution, this is a formula for convolution. It was Conclusion in Kazakhstan worked with this convolution before, but he was kind of guessing this without. So now this is a general theory that we calculate from. So from this formula of convolution, we just calculate this using this formula, rewrite it in the integral. So we define it using Fourier coefficients, but if we rewrite it as integrals, we see it's very interesting, because if H is 1, then we get the usual convolution on the torus. But if H is not 1, then this is it has such integral interesting part, interesting form. H appears, but then there is nice property that we want to have for Fourier analysis, Fourier multipliers, and so on. We want to have the properties that Fourier transform of convolution gives us product of Fourier transform. And so we have, if we define everything correctly, then this is we have this property. No, this is okay. So these are convolutions. So now we have some, so because it's a Riesz basis, we have the well-known property about, we don't have Plancherel formula a priori, but we have these inequalities about Plancherel type inequalities. However, what is interesting, what I want to show is that we can modify, we still can have Plancherel. I haven't seen this in the literature, but it's very simple, so this must be, but let me just say that, so if we define, let's define AB, so these are coefficients, AB are functions of Xi, these are coefficient functions, but we can define L2 product by this formula. A priori, it's not clear that it's an inner product, but one can show that it is an inner product because we take inverse Fourier transform with respect to L of B, and then we compose with Fourier transform with respect to L star. And then if we define it in this way, if we define L2L, the norm in this way, then we have Plancherel formula. Surprisingly, we have the Plancherel formula with equalities. So we can talk about Sobolev space also. We can talk about Sobolev space with respect to L. And we can define LP spaces. So this is interesting because for Fourier analysis, many questions are about LP problems and so on. And so for example, we define LP, these are definitions, and you may wonder why we define like this. But you see, we have U Xi. If P is between 1 and 2, we put norms of U Xi here as weights. And if P is between 2 and infinity, we put norms of V Xi as weights. So you may wonder why this looks like complicated definition, but with this definition, why we have this definition? This we have because then we have Hausdorff-Young inequality, and then we also have this duality that LP prime of L is equal to LP prime L star, and many questions. So I would say, for example, so with I saw Ilya Livland in the audience here, and then who is a specialist on Fourier analysis. And of course, one may say, recently we wrote a paper about rearrangement inequalities, some on groups, and also on the torus, using Fourier analysis on the torus. But here, here we have all basics for the Fourier analysis to ask the same kind of questions for different settings. So we have this. So I just want to say that we have quite a lot of elements of Fourier analysis to ask meaningful questions. So with these norms, and yeah. So now about pseudo-differential operators. So here comes another assumption, which is maybe very natural. So up to now there was only one assumption that we have a model operator L with discrete spectrum, and the eigen functions of this operator form a Riesz basis. So here comes another assumption, namely that the eigenvalues of this operator L go to infinity. That they go to infinity. Basically, this condition is that they go to infinity, and which is a very natural condition. And based in quantitative way, we put that like this: that there is S0 some power such that the series of negative powers of this remember that this size, these normalized eigenfunctions of operator, but because there is eigenvalues of operator, because we put minus S0, so basically it says that the series of eigenvalues to some negative power converges. And under this condition, we can do, so we have a few more things. We have Schwartz kernel theorem. So we can show that there is for any operator from test functions to distributions, which is linear and continuous, we can find the Schwartz kernel K. So here is K. So this is, we can prove the Schwartz kernel theorem that we have a in Schwartz kernel K. And because remember we have a convolution, then we can also rewrite this as a convolution kernel. So we have any operator A, which we can write as a convolution with respect to L with some kernel, which may depend on X. So this is natural because there is no invariance a priori. So we can have this. We have this convolution, but this is a big step because this is very much in parallel to the classical theory of pseudo-differential operators, because now we can define the symbol of the operator. And in the same way as is done in the classical situation, once we have a convolution kernel of the operators, the symbol is the Fourier transform of this convolution kernel. So the symbol, we can define sigma A as Fourier transform of Ka of the convolution kernel, which is recalls that this means like testing this on weak side. And then we have a theorem saying that if we define the symbol in this way, then we can quantize operators like this. So then A of x we can write in this way, using this new Fourier analysis and new symbol. So now we are in the position to start the theory of pseudo-differential operators, because we have a symbol. So we have the kernel, we have the symbol, we have the quantization formula, and we can also talk about multipliers, because now we have the symbol. If the symbol does not depend on x, then we can talk about Fourier multipliers in this situation. So I show you some results here. So we have so Fourier multipliers, let's start. This is a classical question. One of the important questions for Fourier analysis, what about properties of Fourier multipliers? And so we can define here Fourier multipliers. We can say that the symbol does not depend on x, or we can say that alternatively, we can say that this is once we take Fourier transform of f, then it multiplication by m of xi on the Fourier transform side. So, and then we can ask basic questions, like what about LP boundedness theorem, what about LP-LQ boundedness? And as I said here, so already with Niyaz-Tokhmagomedov, we had Hausdorff-Young inequality. So LP prime, continuity of Fourier transform. So that's why you see this weak psi and u psi in norms. LP prime norm is defined like this, because we put weak psi and u psi here. And once we put u psi and weak psi, then we have this Hausdorff-Young inequality. So Fourier transform is continuous from LP to L prime, LP to LP prime. If LP prime norm is defined like this. But as I said, if we define it like this, then these LP spaces become nice interpolation spaces, and also they have duality and other properties. And then we have okay, so this, and then we have so we have Paley inequality. I think some people call it Pitt inequality in Fourier analysis, but we can say Paley inequality here is that it's a technical inequality. I will not give you much detail, but what I want to say is that this inequality gives us LP-LQ multiplier theorem. And this is a method which goes back maybe to implicit to Hermanda, but recently I worked on this with some colleagues, also Kazakhstan. So we have a version of Paley inequalities on SU2 first, then on general with Akaljanov and Nursultanov. Akaljanov was my PhD student. Then on symmetric spaces, on homogeneous manifolds, we also have on quantum groups. And recently also with Akaljanov, we had this kind of inequalities for Neumann algebras, but I don't speak about this here. But basically, once we have this is LP. So we have LP-LQ Fourier multiplier theorem. This is one of the recent results. Basically, it says that it gives conditions that if you have this operator A is a Fourier multiplier, its symbol is sigma AL of xi, then if this sum is here, the sum is finite, then the operator is bounded from LP to LQ. So this is an analog, one can say, Hermanda LP-LQ multiplier theorem. Now in this set, because Hermanda had this theorem on our LP-LQ multiplier, but so this is an analog of that theorem in this setting, and we can extend this to pseudo-differential operators because we also have Sobolev embeddings in this setting, and we can also apply this to some nonlinear equation PD, which I will not talk about here. But basically, we'll have LP-LQ multiplier theorem, and then also we have LP-LP multiplier theorem, like Miklin-Hermanda theorem. Maybe I'm maybe run a little bit out of time, so I will say that we have some additional assumptions, like we assume that there is some order so that we have while eigenvalue counting formula for the operator, which is a natural. Well, we always have this formula. It's just so Q is like an operator. Q is the order of the growth, we can say, of the eigenvalue counting function of the operator L, and then so here maybe may look a bit technical, but just I say here that we have a version so of Michel-Hermander multiplier theorem and of Marcinkiewicz multiplier theorem for LP boundedness. So if some conditions on the symbol are satisfied, here you can recognize a little bit in one. This is kind of similar to Michel-Hermander type, to Hermander type of Hermander version of Michel theorem, and second one Marcinkiewicz, then operator is bounded on LP. So this is LP boundedness. This is about Fourier multipliers, but now let me talk about pseudo-differential operators, as in the title of this talk. So the question is how to define symbol classes. So if you want to have a calculus of pseudo-differential operators, then we want to define symbol classes, and then we can talk about compositions, and we can solve differential equations. If you have a notion of ellipticity in these symbol classes, then we can solve partial differential equations for elliptic operators. And so here it's a little bit technical, but let me say that it is an extension of, because I mentioned that I worked quite a lot on groups, and on groups the problem is that the dual variable, as I mentioned, that we define f hat of xi, and xi is a representation of the group, and then we cannot differentiate with respect to xi like we do in Rn. So we have to do something else, and then so in those works we develop a notion of difference operator, which acts on the dual variable and which replaces derivative with respect to xi when we are on Rn. And here we kind of make an extension of this to this setting. So we define. So let me say. So we fix some collection of functions Q, which will give us. Maybe I will skip this a bit. This may be a bit technical, but let me come to the conclusion. Basically, we can define difference operators. This is a complicated formula, but we can, using this formula, we can define difference operators with respect to xi. And the interesting difference with pseudo-differential analysis on Rn or on groups is that these difference operators, they act on Fourier coefficients, but they depend on x. And once we define these operators by those complicated formulas, but those formulas, they look complicated, but they are necessary if you want to have a good calculus. And indeed, we obtain a very good calculus for these operators. We can define symbol classes like this. So dx are, we can think, derivatives. So a is a symbol defined before. X are derivatives because x it's a manifold. We are on a manifold, so we can differentiate with respect to x. But we take these difference operators. They act on the variable xi, but we write x here in brackets to emphasize that they depend on x. Although they act on xi, but they are dependent on x. And then we can define rho delta classes of Hermander. We can define the usual one, SM class of Hermander. And so these formulas, so if we are on Rn, these formulas reduce to derivatives. If we are on the torus, then these formulas reduce to difference operators on the lattice. But they are for these general operators. So on Lie groups, we can. So on groups, these operators do not depend on x. But this is because we have a group structure. Here we are in non-harmonic analysis situation. So we don't have any underlying structure. We don't assume any underlying structure. That's why these difference operators, they are in xi, but maybe x dependent. But anyway, so once we define these difference operators, we have definition of these symbol classes, and then we have a nice calculus saying that, so suppose we have an operator in this symbol class, then the adjoint operator here, A star, will be also in the corresponding symbol class, but here again we keep track that this is quantization formula with respect to L. So if A is in the symbol class Sm with respect to the L quantization, then we can prove that the joint operator is in the symbol class Sm tilde with respect to L star quantization, where the class Sm tilde is defined in terms of this Sm. And we have a asymptotic expansion for the symbol of A star. And the formula here coincides, if you are familiar with the pseudo-differential theory on Rn, then this you will recognize. This is the usual formula on Rn. This is the usual formula that we want to have. Composition formula. So if you have two symbols in two symbol classes of order M1 and M2, then the composition is again in the symbol class of order as M1 plus M2 here. And we have the asymptotic formula for the composition. So we have this is more recent. This is a paper on arXiv this year. We have a notion of ellipticity. What symbols are elliptic? So then which operators are elliptic? Then if you have elliptic symbols, then we can find parametrics. So we can also talk about functional symbolic calculus, and we have Gordian. So in application, we have Gordian inequality, which is a lower bound for operators with positive symbols, and this is important for solving differential equations, which I will show. Sorry, now I'm maybe skipping some things, but this is so we have a version of Calderon-Vaillancourt theorem, boundness or two boundness of operators of order 0, but this is application to Cauchy problem. So suppose we have Cauchy problem, you can think of parabolic problem with boundary conditions. So now remember that the boundary conditions are embedded into this calculus. So embedded into definition of the symbol classes. So if K is some operator in this symbol class, and boundary conditions, as I said, are embedded in this symbol class, so satisfying boundary conditions which were given, then the theorem says, as an application of the Gordian inequality, and so this is real application of the pseudo-differential calculus to partial differential equations, we say here that there is unique solution, and we have some a priori estimate for this solution. So it is an application a good example of application of this calculus to concrete partial differential equations, which we can now solve. We can prove well-posedness with fixed boundary conditions using this calculus. And I can mention a little bit. So this is we have so Gorbek lemma. I guess in this so in this seminar, people familiar. So Gorbek lemma is measures distance between operator to compact. So how much operator is non-compact? So T sigma is our operator, and K is a compact operator, and then so we prove a version of Gorbek lemma saying that we have a lower bound of distance between operator to the space of all compact operators, which is given in terms of symbol. So compactness, in particular, we have this gives us criterion of compactness. So operator is compact if and only if its symbol goes to 0 at infinity. So this is similar to the usual case. And then we also have Gershgorin theory. There is a so-called Gershgorin theory of spectrum localization, which tells us so where the spectrum of an operator is. And so here we have a version of Gershgorin theory for our setting. Basically, there are so-called Gershgorin disks. It says that if there are some conditions satisfied on the operator, on the symbol, then we can tell that in terms of these conditions, we can tell that the spectrum consists of some union of some balls with some centers and the radii, and we can find the centers of these balls and the radius in terms of the operator and its symbol. And so basically this is a usual Gershgorin theory, and now we have the version of this for this calculus, so it's a nice extension. This is paper published this year, and so also this is a bit of nuclearity, and we can do spectral theory using this, but because it's sometimes here it's because we are dealing with boundary conditions. So, like if you think about Schatten classes, for Schatten classes we need to compose operator with its adjoint, but they may have different domains. So if you think about singular numbers, so singular numbers are eigenvalues of the operator, of the modulus of the operator, and modulus of the operator we have to compose operator with its adjoint. But if they have different domains of definition, they have like already in the example which I gave with H modification of the classical Fourier analysis, they have different domains. We cannot compose operator with its adjoint because they have different boundary conditions. So then we cannot define the singular numbers in the standard way. But then, fortunately, here we have Grothendieck theory of nuclear operators, and for which we don't need to look at the Schatten numbers, but these nuclear operators coincide with Schatten classes if we're in Hilbert spaces, but it also gives extensions to Banach spaces. And so in particular, we have this notion of nuclearity, nuclearity of an operator between two LP spaces. But if operator X from the same space LP to the same, we can calculate its trace, and then we can prove. So the first is a condition on the symbol. So if this condition on the symbol is satisfied, then this we already had a while ago in this paper, 2017. Then we have this estimate for the Eigen Functions. And more interesting is that if we have this condition R between 0 and 2/3, then we have a Litsky type formula, which means that the trace defined as a integral over the kernel, over the diagonal, the first formula, is also equal to the sum of eigenvalues. So this is in Hilbert spaces, this is the Litsky formula, but by Litsky. But here we can have this is also true for Banach spaces here, and we also in another paper this year, which I don't have time to talk about, but we also analyze Dix-Mir traces, and then also expansion of traces for heat kernel, and for this kind of cutoff. So then this is gives some implication with so idea to analyze index to write some index formulas for this operator. But I will not speak about this here. So maybe I think my time is coming to the end. So let me summarize. So many results that we had on groups extend to this setting, and but there are some differences. So as I said, the only assumption is that we have basically the only assumption is that we have an operator with discrete spectrum, Eigen Functions form a Riesz basis, and eigenvalues go to infinity. Then for any such operator, we can establish quite good Fourier analysis with Fourier coefficients. Of course, there is a lot of open questions because I would say that we have Hausdorff-Young, Paley inequality, some basic things we establish which we need, for example, to have Fourier multiplier theorems. But there are a lot of other questions of Fourier analysis which haven't been addressed. So I think it's interesting. We have so then we can define difference operators which give us symbol classes, and the different so it's everything is similar to the known theories, but difference operators depend on the point X here in the space. But then anyway, once we have these difference operators, we can define symbol classes, and in these symbol classes we have full symbolic calculus, compositions, adjoints, functional calculus, ellipticity, parametricis. We can also talk about hyperellipticity in these classes, and we can apply it to differential equations. And so again, I want to say, as last words, that general philosophy here is that when we are encountered with a problem with some complicated boundary conditions, not complicated, but which are with some boundary conditions and or operator with some domain, like harmonic oscillator on the whole space, which we can decompose in terms of Hermite functions, then it is more convenient, maybe more convenient to work in terms of Eigen functions of this operator rather than using classical Fourier analysis. And so this is the idea that we are trying to develop here. So I presented you results which we have at the moment. And so I think that's the last slide. So thank you for your attention.
Thank you very much, Michael. Very interesting. Thank you. Please, if there are questions.
Yeah, I have not a question, but I have some comments.
Yeah, please.
I have really. Do you hear me? Yeah.
Yes.
Yes.
Yep.
Yeah, I have, of course, followed Ruzhansky on distance, and I'm very impressed of your lecture. We have looked to have lived a little parallel here, you know. We have been very interested. We have written books about hard inequalities, and we have worked very serious with harmonic analysis and all inequalities there, you know. But originally, I was also very interested in pseudo-differential operators. You know, Hermander inspired me a lot, of course. But I have not followed, you know, this. So therefore, this lecture was especially interesting for me to see you do all these things. And other things I have observed about you is that this to work with metric spaces and this lately, this I'm very interested in also to polar coordinates in metric spaces you have introduced and worked with. And it looks to be very fruitful. You get new applications. And we look to have also both of us very close connections to Kazakhstan. So those who refer to Tupan Gambetov, you know, is also, and his brother, you know. And Nursultanov is also a very good friend of me and his wife, Nazarki, and Oinarov. And I'm honorary professor in Kazakhstan also, so we look to have also, so we will of course meet someday. It looks so. So I only wanted to say this, and I have some very concrete also there connected to your results, connected to Fourier inequalities there, you know, Hausdorff-Young's inequality, you know. Because in the classical situation, I have very good feeling what happens there, you know, and you know, you must, to get it really better inequality, you must take the corresponding Lorentz space, not LP prime, but still it's sharp with the constant. But if you look from functional analysis point of view, but then you must have something like rearrangement also. So I think it's more things to do there, which could be of interest, but maybe people have already done it. But it's only one thing, but it's a lot of thoughts I have during your lecture. So thank you very much.
Thank you. This is indeed, indeed, I thank you for mentioning some other works. Indeed, this hard inequalities in metric spaces with polar decompositions, we followed your ideas from your papers also. So I know many of your works. So we haven't intersected yet, but maybe in the future. But indeed, there's questions about Lorentz spaces and so on. These are open, I think, for this kind of Fourier analysis. Basically, I showed you most of the things that you know about Fourier analysis of this type. But as the classical Fourier analysis is an enormous subject. And then all these questions that people study in Fourier analysis make sense in this setting. If you put H, already in the simple situation, if you put H, we get a version of Fourier analysis. It can be reduced to the standard one if you talk about H, but if you, for other conditions, it cannot. So if you put H, simply we can reduce. But another example, which I put non-local condition, we cannot reduce. So that's why it makes sense to consider these questions independently.
And interesting to see we have also Rabinovich as a common friend.
Rabinovich, of course, is when I talk about the torus, and I
Yes.
should mention there are many papers by Rabinovich and Roch, and then, of course, they didn't use exponential functions, they use some powers, but basically it is the same thing, and they have many interesting results. But that's a special kind of kind of falls into this. But we have another paper on pseudo-differential. I was surprised that on the lattices. In the papers of Rabinovich, well, he's here. I see, but he had Calderon-Vaillancourt theorem, some estimates, but not really the full calculus. But we have recently established full symbolic calculus for the operators on the lattice and symbol classes and so on.
Okay, thank you. So if there are more questions or comments.
I have the questions, some questions.
Yeah, please.
Okay. So my question is following. You consider the case when the pseudo-differential, basic pseudo-differential operator has a discrete spectrum, but there is a lot of very interesting problem decomposition where the basic operator has the discrete and continuous spectrum. But my opinion, all difficulties in the calculus of the pseudo-differential operator is the calculus on Rn, because in this case we have the symbol of the operator is the product Rn by Rn. This is some difficulties in estimates and something like that. If you consider only the discrete spectrum, the part of these difficulties disappear. What do you say about this problem?
Yes, this is very good question, but I would say that because there are only 24 hours per day in a day, so we cannot consider all kinds of problems. So we start. So this is the first step, I would say. The first step was to start with discrete spectrum, in which case we can consider, we try to see what we can do. And we developed quite a full theory in the case of discrete spectrums. And the next question is, of course, we can still have discrete spectrum, but we can have some associated Eigen functions. This is one possibility. We can have some continuous spectrum, which is another possibility. So here, different technicalities appear. So I have some PhD student now, he is dealing with Dunkel operator, which is kind of a model case where you can have, you can try to do things also explicitly. But I would say that this is a good question, and this is certainly kind of in plan to work on this. But it is not that it's not possible to do. It is just that nobody tried to do it. So this is the main. This is the situation at the moment. But certainly these are interesting questions to consider.
Okay, thank you. More questions or comments? So it doesn't seem the case. Then thank you very much, Michael. Once again, it was very interesting. Thank you. Great talk. There is Dmitry. No. There are no questions.
No. I think the Gerard may have question. Let's see. But I cannot hear. I cannot hear. Gerard is saying something, but I cannot hear him.
I'm not sure.
Yeah. That's okay. Yeah.
but really it was very interesting, and so you developed the whole theory. Was really impressive.
Thank you.